Log on, tune in, find out. Another good idea from Cambridge.
The schematic of Narasimhan stratification.
Thank you very much for inviting me to give this talk. I'll describe the geometric situation which will hold for the first part of this talk. Reference for the first part of the talk is archive 0909 0891. This gives the schematic okay, so this will always involve a projective morphism. This is a Noetherian scheme and this will be equipped with relatively ample alignment. Now, given any spec k into S, consider the projective scheme xk and stick this there, and then I have coherent sheaf on it E. Recall that this is called a pure dimensional sheaf with pure dimensional support, often just abbreviated into a pure sheaf. If it has the property that on any open set, any non-zero section has support of the same dimension, and that dimension is called the dimension of this pure sheaf. So, pure any sigma not equal to 0 in EU, where U is in this xk, support sigma has the same dimension D, irrespective of which non-zero section on which open set you select. So, that means the Hilbert polynomial of this is going to be of degree D. So, PE in particular, that implies, converse of course is not true, PE, the Hilbert polynomial, is of degree D, and I will write this PE with variable lambda. So, it will lie in Q lambda. Probably at some stage this stops being visible from there, but I have not written anything you need to read. So, this can be written as some leading coefficient lambda to the power d upon factorial d plus lower order terms, and this I will call RE. For vector bundles in nice situations, this being the rank, we will call it rank of E. Okay, so recall that something is called a Giesecker semistable if for every coherent subsheaf of such a pure sheaf. First of all, to qualify for the word semistable, a sheaf has to be pure, and then for every coherent subsheaf, the Hilbert polynomial divided by the rank has to satisfy the usual inequality, which I do not have to write here. So, for this one has to remember that if I put q lambda on this axis and z, then this q lambda is totally ordered. Q lambda totally ordered by saying f is less than g means f m less than g m for m sufficiently large. And then in general, if I have pure dimensional sheaf, it has a unique harder Narasimhan filtration. So E is pure dimensional. Then it has a flag of coherent subsheaves. Being its subsheaves, they will of course all be pure dimensional of the same dimension D. And they have the property that the corresponding Hilbert polynomials of the graded pieces decrease. So, if the Hilbert polynomials are f1, f2, f lambda, this means fl, then a picture of this kind is usually drawn. Such a filtration is unique and semi-stable means the length L is just 1. Now, Schatz studied the variation of this. So, this is called the harder Narasimhan type. So, remember this coherent sheaf was on some point in S. One may have such a family which is flat over the base, and then you want to study how this harder Narasimhan filtration type varies as you move the base point. And what Schatz proved, so the variation of the type, he showed it is upper semi-continuous. So, between two such polygons there is an ordering. If the other polygon is something like this, they are not comparable. This is only a partial ordering between polygons. The other polygon has to lie entirely under this, and because Q lambda is totally ordered, this under makes sense. Okay. So, the variation of the harder Narasimhan type is upper semi-continuous. Therefore, if E is now on X and E flat over S, and each, this is coherent of course, and each ES pure dimensional. These are the conditions on the sheaf on X. So, each is pure dimensional and family is flat. Then the result of Schatz gives a stratification of the underlying set. This underlying set becomes the union of where tau varies over possible harder Narasimhan types. And then the lowest stratum is open and the top is closed and whatnot, whatever semi-continuity means. So, the first result I will prove is that these strata, each one of these strata, which is just a locally closed subset in the Schatz theorem, has a natural structure of a scheme which makes it a locally closed subscheme of S, and this stratification has a universal property. So, so first theorem, so before I state the theorem, I need a definition, and that is what is meant by relative harder Narasimhan filtration. So, So, if I have such a coherent sheaf on some x over S, a relative Harder-Narasimhan filtration will mean a filtration by subsheaves such that each, so this is E0 if there is any doubt about notation, is flat over the basis, pure dimensional, that will follow of course, and at each S belonging to S, this filtration should restrict to the Harder-Narasimhan filtration of ES. Such a thing I will call a relative Harder-Narasimhan filtration. So, now the theorem. So, first statement is each topological stratum has a unique structure of a locally closed subscheme of S with the following universal property. A morphism T to S factors via the disjoint union of this strata if and only if, okay, I am just talking of one at a time, so I need not write, if and only if the pullback E t which lives on x t over t admits a relative Harder-Narasimhan filtration. Of type, of course, that needless to say since it is factoring through this. Okay. Second statement, if a relative Hn filtration exists for all of t, for all of E, then it is unique. So, this in particular means that on each stratum you have such a unique relative Harder-Narasimhan stratification. And third, if T to S is any morphism, the schematic inverse images of the S tau give T tau with the above properties. which means the stratification base changes. Okay, so let me show you the proof. So, for the sake of the proof, I need some elementary basic properties of Narasimhan filtration and how it rises. So, here are a few properties which I will recall. So, first of all is open in S. Okay. By the results of Schatz, tau only rises. So, something that much and smaller is always open. And this means that is closed. So, my strategy is going to be I am going to take everything below a certain level, and the one on which I want to give the structure of the scheme is then the top stratum. So, one may think, and naively one would imagine that you begin with the lowest one and call it open and then go to something and add in next one by one. Instead of that, I am saying go to the top and bring it down, define the smallest one first. Okay. Second thing I want to recall is, suppose E has type, this is one property, another property, if E has type tau equal to F1 Fl, and if E prime is a coherent subsheaf such that and I can even say less than or equal to this, suppose type is less than or equal to this, such that the polynomial of E prime is actually F1, then E prime is the first step of the Narasimhan filtration, and the type of E mod E prime is less than or equal to F1 minus, sorry, yeah, I should begin with F2 now, F2 minus F1 dot 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 Fl minus F1. This is the second fact. And the third fact is Giesecker semi-stability is preserved under field extensions. And therefore, Hn type okay. So, before I prove this theorem, okay, these are the properties of Narasimhan filtration I will use in proving the theorem, and I need one more lemma which I will now state and prove. And then armed with this lemma, this, and then we will do some deformation theory and we will get the theorem. So, the lemma is this. Suppose S is Noetherian S and T Noetherian, and let F T to S be a morphism. Then F is a closed embedding if, and of course only if, the following so what are these properties? I want F is proper injective, unramified, and induces isomorphisms on all residue fields. Upstairs of T. Okay. Should have these 4 properties, and then it's a closed embedding of schemes. Let me prove it. So this proof of the lemma, this is local. So I can assume S equal to spec A a Noetherian local ring, and then proper injective finite morphism, therefore, and also only one point above my closed point. Therefore, I can also assume by the conditions, I can also assume that T is equal to spec B, where B is a local A algebra, finite over A. And now the 2 conditions on the residue field and being unramified mean A mod M A is equal to B mod M B, this because the residue fields are the same, and now unramified M B is equal to M A times B. Therefore, by Nakayama, A equal to B, or rather, how should I say, A to B is surjective. Okay. All right, so that proves the lemma, and so now I will prove the theorem using these three properties and the lemma I will use to prove the theorem. Which? Yeah, but as you will see, my arguments entirely depend on code schemes and their deformation properties, so I cannot make them for mu. Okay, so the idea of the proof is I begin with this S and then I take, so proof of theorem. Let S less than or equal to tau be the open subscheme. So to the open subset, I just give the open subscheme structure, and now tau is my top stratum there, so it is something closed. So of these properties, I am now using the first one there. And now I take the code scheme the relative code scheme how should I write it? Code of x less than equal to tau over s less than equal to tau and okay, so I should invent more and more notation. By x less than equal to tau, I mean the inverse image of s less than equal to tau, and E less than equal to tau is the restriction there. And on that, I want quotients of this which have the Hilbert polynomial of FL minus, it should have the Hilbert polynomial FL minus this with respect to OX less than equal to tau 1. This is the code scheme. So, if I take this code scheme, which means this parameterizes subs which have the Hilbert polynomial of the first step of the Harder-Narasimhan filtration. If one looks at the kernel of this, kernel of the universal quotient on this code scheme, that is the subscheme of the type of E1. So, all through this I have an E1, and I am going to show that this map pi satisfies the lemma. Okay, why does pi satisfy lemma? It is proper because any code scheme is projective, injective because set theoretically Harder-Narasimhan stratification filtration is unique, unramified I will come to in a moment, induces isomorphism on all residue fields because, as I said, Giesecker semi-stability is preserved under field extensions. So, if you have the Harder-Narasimhan stratification of something upstairs, you pull up the sheaf and upstairs there is Harder-Narasimhan stratification, that comes from below. Such a stratification comes from the base field, and therefore, if I take a point in the code scheme, the quotient is really defined below, the residue field above therefore equals the residue field below. And now, once I show the residue fields are the same, unramified boils down to the vertical tangent being 0. The vertical tangent, which means I am going to vary the sub or the quotient whichever you see, as you know well from the Rachmaninian situation, various elementary situations, the tangent is the home of the sub with the quotient. And one of the properties of the Harder-Narasimhan filtration is home Hn1 E, comma E mod Hn1 E is equal to 0. The first part is more positive than the later part, nothing of 1 about special about 1, you can go to some level and then take its home in the rest. So, this shows that the vertical tangent vectors are 0, and therefore, all the properties demanded by the lemma are satisfied by this scheme. So, so this is by properties of Hn filtration plus fact about tangent to a code scheme. Okay. So, what does that show? That on Q, now I go to the canonical quotient, and the canonical quotient, the universal quotient, on Q has Hn type F2 minus F1, Fl minus F1. So, the length of the Harder-Narasimhan filtration has decreased by 1. So, the first step is canonical, of course, this morphism being unramified, it has, if at all it has a section, it has only one section. So, the first step in the Harder-Narasimhan filtration, when it exists, is unique. In a relative Harder-Narasimhan filtration, if the first step exists, is unique, this much we have already shown. Going moduloid, the length of the filtration is less. So, by induction, the theorem is true on Q, and Q embeds in this S less than or equal to tau as a closed subscheme, and therefore, now I have the filtration on S tau. Okay. So, this is the proof of the theorem. All right, since I have given you the reference to the archive, I will not write down the proof, but I explained the whole idea. Now, let us come to the first corollary. So, I will write it there. Corollary. If S is reduced and Harder-Narasimhan type of ES is constant tau on all of S, then S admits a unique relative Harder-Narasimhan filtration. Okay. So, now I am going to apply my theorem to get consequences. So, the first consequence, the corollary is obvious, because any closed subscheme of a reduced scheme is itself which has the support all the points. Okay. Because the Harder-Narasimhan filtration is constant, the support of the only stratum is everything, and if I have closed subscheme of a reduced scheme which is set theoretically the same, then it is the same. Okay. So, now I will prove consequence, which is theorem 2. So, let be the stack of coherent sheaves on X over S. This means, recall that this means objects of given an S scheme T, the objects of this are coherent sheaves on X T that are flat over T. Inside this, because purity is a Zariski open condition, therefore, inside this I have an open substack of pure it's only a pointwise condition, therefore, it behaves well with respect to descent. All right. Now, what I get as a result of this is locally closed substacks I have to define these stacks first as a groupoid. As a groupoid, the objects of this over T are all those families of flat sheaves over Xt which are pure at each point and admit a relative Harder-Narasimhan filtration of type tau. Now you have to see this groupoid is indeed a stack, which means the relative Harder-Narasimhan filtration has to satisfy the necessary descent conditions. Now one of the important things in proving a descent condition is the uniqueness of gluing, and that's where the theorem helps in showing that if after base change there is a relative Harder-Narasimhan filtration under some flat morphism, under some FPQC morphism, you pull back E and there you have Harder-Narasimhan relative Harder-Narasimhan filtration, then it must come from below, because upstairs it is unique. So further pull it back to the two-way fibered product and it will be equal, physically equal, therefore will satisfy the co-cycle condition. So co-cycle condition is always held by uniqueness like this, and so it will descend under faithfully flat descent and will give you the relative filtration below, showing this is a stack. Now you want to show the stack is algebraic, so you need an atlas, a smooth atlas, and a smooth atlas for the stack of coherent sheaves itself is provided by a code scheme. See the book of Lomo-Morebai, and in that code scheme my theorem will carve out locally closed subschemes. The scheme. Huh?
Curves are different.
What?
No dimension consideration on this?
No, none. So if you look at the code scheme, in code scheme Lomo-Morebai define a certain open subscheme where some cohomology vanishing enough positivity blah 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 holds, and then that's a smooth atlas for the stack of coherent sheaves, and in that code scheme, which is a scheme after all and has its universal quotient family, that to that universal quotient family you apply the theorem, therefore the code scheme will get stratified by locally closed subschemes, and the locally closed stratum number tau will be the atlas of this, proving this is algebraic. So theorem all these are algebraic stacks. Okay, this is the second side. Now I come to the third part of my talk, where I will go to curves, and this third part began as joint work with Leticia Brambilla Paz and Osvaldo Mata, who I am glad are in the audience, and what we earlier wrote is I keep giving archive references, so let me give. So in this paper we looked at various moduli of rank 2 unstable bundles on curves, fixing various data like Harder-Narasimhan type, fixing their assuming they are indecomposable, fixing some more numerical data. Okay. So what happened was, in the past few days I had to began rethinking about this for some reason, and in the last few days I arrived at a somewhat new perspective on the whole thing. So what now I am going to report are the results I have proved in the last few days, actually this week. Okay, actually yesterday, the theorem that now I am going to state. Okay, so here is my theorem, but before I begin, let me tell my philosophy, which will sound very naive, but the theorem is precise enough. Okay, so first, I might as well now get rid of this part. So first let me make an observation for curves, which won't come as a surprise, though of course the stack was not there till I proved its existence, but the deformation theory was there, and so now I will say make a remark about that stack which won't come as a surprise. So now x will be assume always geometrically irreducible, or even better assume k equal to k bar to make life simple. Okay, take such a curve and take some tau to be an unstable Hn type. Then my first observation is the corresponding stack need not be unstable. Any Harder-Narasimhan type is smooth over K. The reason for this is so these are pure sheaves, of course. So either these are torsion sheaves or vector bundles. So torsion sheaves is trivial case. Let's talk about vector bundles. If you take a vector bundle and Harder-Narasimhan type, it may be even the semi-stable one. Then of course you know it's smooth. But any Harder-Narasimhan type, you know the tangent is given by H1 of end prime of E, where end prime are endomorphisms which preserve the so infinitesimal automorphisms, tangent and obstruction are H0 of x and prime E, H1 of x and prime E, and H2 of x and prime E, and this is 0 as dimension of x is 1. So if you fix a Harder-Narasimhan type, you are going to get a smooth stratum, and the normal to the stratum coherent tau x by k is normal to H1 of x and double prime E, where and prime E preserves, this is the sheaf which preserves. So I have to carefully distinguish between sheaves and global Hn filtration, and n double prime E, I have to speed up. So this is smooth. Now I want to understand this smooth stack. So I thought naively, how does one understand any stack, some unknown stack, how do you understand it? And then you try to stratify it into something simpler, stratify it into gerbs, and on this the standard textbook didn't shed any light. And so I thought, being a differential geometer at heart, let me study it differentially. So my idea is, given an unknown stack, take its cotangent complex and try to stratify using the fitting ideals maybe of the differentials in the cotangent complex. Now how do you do that? So if the cotangent complex is perfect of finite length, then you begin anywhere and just take all the determinantal ideals defined by the differentials in this perfect complex. And certainly in my case, the stack being smooth, I should be able to do this. So if I take the cotangent complex, of this stack and try to analyze its differential, I will get somewhere. So this I do in the rank 2 case, and I get results which now I will state, and they in particular shed a new perspective on that paper. So I will also be able to explain what is done in that. So here is the theorem, and in order to prove that theorem, there is one more little surprise it was to me, which I will state at the end. It seems I am rapidly running out of time, so let me speed up. So this is the theorem of yesterday. let the Harder-Narasimhan type be 2 d and d prime is greater than d by 2. So this is rank, this is degree, and this is the HN type. So this means I am thinking of vector bundles of this kind. And this is one of the unstable strata. Okay. Let okay, so I should include some notation. Let making the tau, I am just writing out what the tau is. So take various minors of the differential and take, and then the theorem is, this is the hypothesis, I have not yet come to conclusion. They keep falling off. Yeah, they keep falling off or going off. Then each 1 x 2 d d prime r is a Zariski job so this gets indexed by r, and what happens is okay, the smaller strata are open and the larger are closed. Yeah, this is a semi-continuous stratification indexed by integers. What one gets is a Zariski job over this is a unusual thing. So each one of them is a Zariski job over a quasi-projective K scheme. Okay. Which is not necessarily reduced or connected. So this kind of stratification with non-reduced jobs is a bit unusual. Also the bases are quasi-projective with a smooth, affine, commutative group scheme of automorphisms for each object. The decomposition is canonical in the sense that any other such stratification, so I shouldn't call it decomposition, I should call it stratification. Stratification, any other stratification into gerbs with flat automorphism groups, group schemes for objects will be a refinement of this. So, what is going to turn out is that the basis for this gerb structure are the moduli spaces which are described in that paper, and they are made using the results of Lange. So, I will come to describing these gerbs and their structure after I reformulate the result of Lange, and then it will be clear what is meant. Okay. But this statement I suppose is clear enough. I hesitated to call these smooth affine group schemes as the inertia stack because the gerbs may not be neutral. If the gerbs were neutral, I would have said the inertia is smooth, commutative, affine, whatever. So, there is clearly an obstruction in H2. Okay. All right. So, now let me therefore come to reformulating the result of Professor Lange, who is also here, it so happens. So So, before that, let me just say that each of these gerbs is itself going to be an open union of two gerbs, 1x split 2d t prime r union open disjoint union. So, I should write it as a co-product. 1 indecomposable x 2 d d prime r. It is these objects which occur in the earlier paper, the right hand ones, and these are going to be certain GM gerbs or Picard. This is a Picard gerb actually, and this is going to be gerbs manufactured via Lange's theorem on gerbs, which I will now state. So, the setup for Lange's theorem is as follows: x to s is projective, and there are two coherent sheaves, F G coherent sheaves, flat on S. And then consider the stack. E is the S groupoid with ET objects of ET. So, given any T to S, the objects are extensions of this kind, 0 to GT tensored with some line bundle which is pulled up from T. I copied it from your paper. Okay, so you don't have to write it. ET and morphisms. So, if I have another such GT tensor pi t upper star L prime to E prime to Ft to 0. The morphisms are supposed to be identity here, and here it is supposed to be identity tensored with identity on G, Gt tensored with some isomorphism here and of L, and okay, in good cases I can assume this to be cohomologically flat. I suddenly began to bother about isomorphisms of pi lower star versus isomorphisms of space. In my case, the difference is not going to matter. Isomorphisms of this kind, okay, these are the objects and these are the morphisms. The reason why Lange needs this line bundle is, if one takes these to be the morphisms and tries to do descent, automatically such line bundles will turn up. So, even if you had not put in the line bundle and stackified this, the line bundles would have been born. So, he puts them in right from the beginning. Okay. Now, so let's make, so now let us state the theorem. This is from Monday. Suppose the following conditions are satisfied: x 0 f g, and this is the relative x. I will make a few remarks on this. This is via theory of Kleiman. Just as there is the Grothendieck theory of semi-continuity complex, Kleiman has a theory of a similar complex for relative x, and it works in the projective case. I do not know whether it works in the proper case, but you only quote it for projective, and that is all that was. So, suppose that these two f and g spatialize correctly at each s belonging to S, and therefore, by Kleiman complex both are locally free and base change correctly. Arbitrary base changes. So, when that happens, the following holds. Then these are the assertions of the theorem. 1, this is an algebraic stack. 2, let P be the projective bundle of lines in x1 pi f g. Then there exists one morphism of stacks A from E to P which makes E a Zariski job over P. Next, there are 4 properties which he has. Okay, I am now worried it is going to get. Okay, third property, and I am nearly running out of time. The job has a global section on treat this as an actual physical vector bundle, spec of the symmetric algebra of the dual, and remove the 0 section. And the fourth property is this gerb is neutral in particular when x 0 this last statement is his corollary 4.5. Okay, so this is the Lange theorem, and now let us apply the Lange theorem to our situation. So, I have now, oh dear, run out of time, so I will rapidly in 2 minutes tell you rest of it. I always miscalculate the amount of time. So, okay, what happens is this decomposition, something open, something closed, the openness of this one comes from semi-continuity, the openness of that one comes from the extension being non-split. So, both are open. This was a real surprise to me a few days back. Then this of course is obviously O direction L and a simple structure or Picard. For that one can rewrite the bundle to bring it in the Lange form by tensoring back with L2 inverse and bring it into the Lange form where there is identity. To get that map identity, there is a Picard factor which goes out. Rest of the stack, so that stack is now a product of a stack in which the second map is identity times a Picard, and that stack fulfills the conditions of Lange's theorem, where the base space S is a certain Brill-Noether locus in the Jacobian. And if one calculates the cotangent complex and its derivatives and ranks, what one gets is the stratification, flattening stratification for the Grothendieck Q sheaf of end E. And I remind you that Grothendieck Q sheaf for any coherent sheaf upstairs in the semi-continuity setup is you take the semi-continuity complex, take the 0th to first differential, take its adjoint and take its co-kernel. That specializes correctly, and that is the Grothendieck Q sheaf. More on this Grothendieck Q sheaf and its universal properties you can find in FJ explained, and EJ is full of its various uses. Okay. So, and then finally this flattening stratification for the Q sheaf of end E equals exactly the condition on x1 which Lange needs, because of the following great coincidence which only happens in dimension 1, namely because the Grothendieck complex in a relative dimension 1 situation has length exactly 1, the flattening stratification for the Q sheaf is also exactly equal to the flattening stratification for the first direct image. Okay. So, that is the proof, and I will therefore stop here.
Questions? It's not unnatural to ask for schematic mu or HM filtration.
It's reasonable to ask. My only difficulty there is the theory of code schemes is designed to handle the Giesecke, and Giesecke's strategy is natural for
using
that.
restriction theorems?
I don't know, therefore, maybe, who knows, but I can't see any obvious way of changing and discarding all the other coefficients of the Hilbert polynomial and just concentrating on one of them.
We will have to choose a common for regularity.
That anyway you will have to choose. That anyway takes place because of flatness
So for
and
the curve,
Noetherianness.
no, after restricting to a suitable curve, ideally, you choose.
Achha, you are thinking of restriction. Okay. So your strategy is use the semi-stable restriction theorem, and
On a curve, of course, you know they put.
yes, and maybe in a certain chunk of the Hilbert scheme it can be done, and then in another chunk you will use another restriction. Who knows? I have not thought about it, but yeah.
Any more questions? Okay then, so shall we thank the speaker again?